All right, so today we're going to learn about what are called potential energy curves. All right, so what is a potential energy curve? Well, potential energy curve is just a graph that shows you the potential energy of an object as a function of its position. So simple examples would be to look at GPE and APE. So let's look at gravitational potential energy. I'm going to call it UG, potential energy of gravity. All right, and so the idea is the potential energy depends on vertical position, right? And so we know that gravitational potential energy is mg times the vertical position. So this is just going to be a linear function as a function of y, where mg is your slope. And so it's just going to look like this, right? Just a nice slope there, or a nice straight line where your slope is just mg, right? Notice your intercept is 0, okay? Now, let's take a look at elastic potential energy. So for elastic potential energy, it again depends on position. This time you can have negative position, which I guess is true of gravity also. All right, but so elastic potential energy is 1/2 kx squared, right? So if x is 0, your potential energy is 0. And then from there it looks like a parabola, but it's symmetric going either way, right? Okay, so these are two potential energy curves. All right. What we're going to be dealing with, though, is theoretical or otherwise types of potential energy that give us, very strange-looking potential energy curves. Okay, maybe not necessarily something like this. All right. So some of this we've learned before. So, for example, one of the things we've learned is this: that if you talk about the work done by a force, the derivative of the work, so the derivative of the work as a function of position is simply your force, right? And so the idea is for a conservative force, remember the work done by a conservative force is the opposite of the change in potential energy. Okay, and so that's what this little equation over here says, all right? So in English, what that means is if you take the derivative of a potential energy curve, it gives you the opposite of the force associated with that type of potential energy, all right? So simple example, look. Remember, derivative is slope, right? So here's my potential energy. The derivative of u with respect to position is the slope of this thing, which is just mg. Oh, but that's the opposite of the force of gravity, right? Okay. Similarly, over here, our slope here is always changing, right? So here, the slope is positive. So positive x, positive slope. As your x gets bigger, your slope gets more and more positive, right? Over here, your slope is negative. As your position gets more and more negative, your slope gets more and more negative, right? Let's do this. Let's take the derivative of our elastic potential energy with respect to position, and you get, well, derivative of 1/2 kx squared, 2 times 1/2 is 1, so you just get kx, right? Oh, well, that's the opposite of the force from a spring, right? Because it's negative kx, right? Okay, so yeah, I guess that's that, right? Okay. So that is a thing that we already knew, right? The force is the opposite of the slope of your potential energy curve. So we can find the force f of x from a plot of the potential energy by taking the opposite of the derivative. Okay. All right. Now, so a simple example is, or maybe not a simple example, but so maybe we're given a function like this. So here's our potential energy curve, right? And so the idea is, oh, I just traced that. I'm going to erase it all. So the idea is for this first chunk, our slope is 0. So the opposite of 0 is 0. So that corresponds with that, right? Then for this chunk, our slope is getting more negative, which means the force should be getting more positive, right? Okay. Then for this chunk, the slope is getting less negative, right? So here the slope is negative, it gets less negative, less negative, less negative. That means over here my force needs to be getting less positive, right? Okay, and notice right here my slope is 0, right here my force is 0, okay? Then for this chunk, the slope is getting more positive, which means over here the force is getting more negative. Then the slope gets less positive, which means the force gets less negative. Okay, notice once again that my minimum corresponds to, or I guess my maximum corresponds to a force of 0. Okay. And then you can kind of, maintain this process, right? But I guess maybe the things you need to be aware of is this. Check it out. The places where your slope is 0 corresponds to the places where your force is 0. Okay? All right. So, long story short, if you take the slope of this and plot it over here, and then invert it, flip your positives and negatives, it gives you that force graph, okay? All right, now, equilibrium points. So when you look at a potential energy curve, there are these things called equilibrium points, all right? Equilibrium points are points where the slope of the potential energy curve is 0. They're the points I just highlighted in yellow. Okay? Those are the points where your net force is 0. All right? There are 3 types of equilibrium. There's what is called neutral equilibrium, unstable equilibrium, and stable equilibrium. All right? So if you're in neutral equilibrium and you move the object over a little bit, then it's just going to stay in its new position. All right? If it's in unstable equilibrium and you move it over a little bit, then it's going to feel a force propelling it away from the equilibrium point. Okay, so the example it gives here is a marble balanced on top of a bowling ball, right? If you magically balance a marble on top of a bowling ball and you push the marble over to the side a little bit, gravity is going to pull it even farther away, right? Okay, and then stable equilibrium is the opposite. It's if you displace the object slightly to the side, it feels a force returning it to its original position. So if you put a marble in the bottom of a bowl, and you push the marble to the side, then gravity is going to pull it back down to the bottom of the bowl. All right? So on our graph over here, the idea is here and here are called stable equilibrium. Okay? Because the idea is our net force is 0. So if our object is at this position, and we move it over to this position, the net force is still 0, so it won't feel compelled to move one way or the other. Same thing here, right? If I've got an object at this position, and I move it over to this position, the net force is still 0, so it's just going to stay there, right? Okay, so those are all stable equilibrium. All right? No, not stable. I'm sorry. Neutral. Those are neutral equilibrium. Neutral. That is neutral equilibrium. That's an act. Okay? There we go. Neutral equilibrium. All right. Stable equilibrium. Let's do stable. So stable equilibrium is this point right there is what's called stable equilibrium. So the idea is if I put an object right here and then I push it over to the right, the idea is, so how do I want to say this? So at this point, the slope is positive, which means your force is negative. So the force is going to push it back to that equilibrium point. Okay, and you can literally think of this as, here's a marble in the bottom of a salad bowl, right? And if you push it to the side, the idea is whatever your conservative force is going to propel it back down to the bottom, okay? So it keeps it stable, right? It's not going to fall from that position. Same thing here. If you have an object at the bottom of this salad bowl and you push it up, it's going to roll right back down. Stable equilibrium, okay? So these 2 points here and here are called stable equilibrium. All right, and then finally, this guy up here is called unstable equilibrium. This is the marble balanced on top of the bowling ball. If you put a marble here and you nudge it to the side a little bit, it's just going to roll down away from that blue point, okay? So, yeah, I guess that's that, all right? So did I write this in here? So I guess I should jot this down. So neutral equilibrium, these are places where your u of x graph is horizontal, okay? Unstable equilibrium is places where you are at a local maximum on your u of x graph, okay? A local maximum. So that's this. Locally, that's maximum, right? So if you push it either way, it's going to roll down the peak, okay? And then your stable equilibrium points are local minima. Minimums, if you prefer, okay? So stable equilibrium, I don't know purple pen, so I'm going to do it in green. That's a local thing. Okay. All right, so I guess the last thing we need to talk, oh, so identify the equilibrium points. We already did that, so cool. All right. Now, objects have more than one type of energy, right? We don't have just potential energy, we also have kinetic energy. So last year we would have written that GPE plus KE is TE, right? Well, probably a slightly more technical definition would be, instead of calling it total energy, to call it mechanical energy, all right? Mechanical energy is understood to be the sum of kinetic energy plus potential energy, okay? So we're going to replace TE with E mechanical, all right? And so we can see now how the kinetic energy varies with the potential energy like this. So the idea is, if you want to figure out how much kinetic energy your object has, you just take the total energy, mechanical energy, and subtract out whatever's potential. And whatever's left will be kinetic. All right, so to find the kinetic energy, you take the total and subtract the kinetic. The places where the kinetic energy is 0 are turning points. All right, so here's the idea. So check it out. So suppose I've got this mysterious conservative potential energy. Right? Conservative potential energy doesn't make sense. I've got this mysterious potential energy, right? Okay, and the idea is, if I somehow get my object to a position of 0, then it'll have 6 joules of potential energy, all right? So let's suppose that our object somehow has a mechanical energy, E mech, shoot, I can't write. Stupid smartboard, there we go. E mechanical. Suppose the mechanical energy of this thing is 7 joules. Okay, so what that means is, if the mechanical energy is 7 and the potential energy is 6, that means my kinetic energy is the missing 1, right? Down here, since the potential energy is 0, that means my kinetic energy would be 7 joules, right? Here, at this point, my GPE is 3. That means my KE must be 4, okay? So, but the problem is, just because an object can have a certain amount of energy doesn't necessarily mean it does, right? So like when I graphed this potential energy for the spring, it extends to infinity, right? Like your X can be as big as you want, okay? But how much energy the spring actually has depends on your mechanical energy, okay? So what if the mechanical energy is less than sort of what you can have? All right, the bell is about to ring. I'm going to have to pick this up in a minute. No. All right, so here, I'm going to ask this question to remind myself. What if the mechanical energy is less than 6 joules? All right, I'm going to pause this and finish it after 7th hour. You don't know what I'm talking about. Here we go. All right, so before I get to this, so the question was, what if the mechanical energy is less than 6 joules? I guess let's talk about how that could happen. So the idea, let's go back to the spring example, right? So in the spring example, so we've got this graph, right? So let me give ourselves in the graph. All right, so check it out. So here's our elastic potential energy. The curve looks like this, right? So what this curve represents is how much elastic potential energy you would have at a given position, right? So think about how you can give an object this object energy. You could either, you know, it's a thing on a spring, right? So what are the ways you could give it energy? Well, you could squash it this way and give it elastic potential energy. You could stretch it this way and give it elastic potential energy. Or you could give it a push and give it some sort of kinetic energy initially, right? But the idea is once you let go of it, the only force acting on it now is the force of the spring. And so from that point forward, your mechanical energy will be conserved, right? So let's suppose that at the instant that you let go of it, the mechanical energy is 5 joules. Well, if the only force on it is the spring, then the mechanical energy is going to stay 5 joules. So regardless of what type of energy it has when you let it go, whether you've given it 5 joules of kinetic energy or 5 joules of elastic potential energy, once you let it go, the mechanical energy is going to stay 5 joules. And so what's going to happen is the object is going to oscillate back and forth between this position and this position, right? So the idea is at this point, all of its energy is kinetic. No, I'm lying. All of its energy is potential energy, right? And then it's going to oscillate back and forth, back and forth, back and forth. All right, so in essence, what would be happening is our object is oscillating. I'm drawing this again. So here's our spring. Here it is at a relaxed position, right? So the idea is it's oscillating between here, where you've got a whole bunch of elastic potential energy, but it stops moving, and then it comes back to here, it stops moving, and it's going to just oscillate back and forth, right? And so the idea is at the end points, your velocity is 0, and so all of your energy is elastic potential energy. At the middle, the amount that your spring is stretched is 0, and so all of your energy is potential, or is kinetic energy, right? So it's oscillating. Oh, I'm having such a tough time explaining this. So at the end points, all of your energy is potential energy, right? Then as it goes this way, you lose potential energy, but gain kinetic energy, lose potential, gain kinetic, lose potential, gain kinetic. At this point, all of your energy is now kinetic because your potential energy here is 0, right? But you've got all this kinetic energy, and that carries you this way. So now we're converting kinetic energy back to potential energy, kinetic energy back to potential energy, kinetic energy back to potential energy, and at this point our velocity is 0 again, and so you're going to come back, right? So a little while ago I talked about turning points. So this is a turning point. This is a turning point because the idea is at that point you run out of kinetic energy, and your potential energy wants to convert. I'm sorry, and so you're going to, yeah, you've got all this potential energy, and it's going to pull it back this way, right? So it just oscillates back and forth, just as though this was a marble in a bowl rolling down and up, back and forth, okay? So, what if our mechanical energy was less than 6 joules? All right, so like what if we had a scenario where somehow we gave this object, maybe we started it at a position of x1. So maybe that's here, right? Okay. With no kinetic energy, right? So maybe the mechanical energy is 5 joules.
Good afternoon, Stanford students. Students, at this time.
All right. So the idea is, at this point, our slope is negative. That means our force is positive. So our object is going to be pushed this way, right? Okay. And my total mechanical energy is 5 joules, right? So what would happen is the object would begin at this point. The force would change our potential energy to kinetic energy. So by the time we get down to here, all of our energy is now kinetic. Some of it converts back to potential, back to kinetic, back to potential. And so the idea is, at this point, it's going to just keep going this way forever with a kinetic energy of 1 joule, right? Because we've got 4 joules of potential energy, and so the remainder is going to be kinetic. Okay? What if we started it at this position, but gave it 5 joules of kinetic energy. So right here, my potential energy is 0. And if I give it 5 joules of kinetic energy, well, it would depend on which way I'm moving. If it's moving this way, then what's going to happen is, so the idea is my potential energy there is 0. My kinetic energy is 5 joules. It's moving this way, so what's going to happen is I'm going to gain potential energy and lose kinetic energy. It's going to go up, 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 right? Remember, the idea is, once again, my mechanical energy was 5 joules. So it's going to get to this point. That now becomes a turning point because it can't pass this point. So it comes back down, up over the hill, and you get the same thing we had last time. Okay? All right. What if we started our object right here and we gave it a kinetic energy? Maybe it's moving to the right so that the kinetic energy is 1 joule. Okay, well, let's see. So what would that mean? So that would mean that at this point, our potential energy is 1 joule, our kinetic energy is 1 joule, so our mechanical energy is 2 joules, right? So all that would happen is the object would start here with a joule of kinetic and a joule of potential. As you go this way, your potential energy increases and you lose kinetic, but remember, you can't go above your total energy line, right? So once again, you get a turning point, and it would oscillate back and forth in this little bowl here, right? But it can never go above that total energy line, right? Because you can't have more energy than that. All right? We'll probably have to talk about this in class, but that's the idea. I'm going to stop there. I hope that made sense. Come in with questions. I'm unhappy with this video. I'm going to have to redo it later. There we go. Have a good day.